before we get to the idea of an equivalence relation, we're going to first say what a relation is. So a relation is something that you define on a non-empty set, let's call it S, and it's as the definition is trying to capture, well, exactly what it says, relating elements of S with themselves. So how could we possibly relate elements of S with other elements of S? Well, we need to somehow have something that um, deals with pairs of elements from S. And the right thing here, or at least the thing that works, is it's a subset R of the Cartesian product S cross S. And as just a quick reminder, this is a collection of all S1, S2, such that S1 and S2 are in S. Okay. So it's a subset of this. We don't want to relate every element of S with every other element necessarily. We might want to do that, but in general we won't. But it's a subset R of this product, and this is what a relation is, and usually we will we'll write something slightly different from what's in our book, but we'll write S1 is related to S2 if S1, S2 is in R. Remember, R is some wild subset here, and if the ordered pair, again, this is an ordered pair, so order matters here, S1, S2 is in R, then we'll write S1 is related to S2. And we think, we say it exactly as I said, so let's put here and say S1 is related to S2. And usually that's enough, but if we want to specify the equivalence relation, we might say under R. Or if we want to specify the relation, we might say under R. So let's do a quick example. Equals is a relation. So what is equals? What is that as a subset of S cross S? Well, if we let R be the collection of S comma S, where, oops, I'm using the colon, sorry, where S is little s is in big S, then that is certainly a relation. And S is related to T if and only if S comma T is in R, but that happens if and only if S is equal to T, if they're the same element, because to be in R you have to have the same first coordinate as your second coordinate. So this is an example of a relation, and this is a relation on any set. Sort of the highest form of equality on a set. Now, let's call that A. Let's do some other ones. So let's suppose we had the real numbers here is what it was our set, or the rational. I guess this is a algebra class, so let's do the rational numbers. Or heck, we were just dealing with integers, so let's even do the integers. But suppose you have a set that is ordered, okay? Then we could let R, well, what relation are we going to try to define here? We're going to write less than or equal to. And it's defined by the following subset. All right, so since we're using integers, let's use A for our elements here. So A1 and A2 should be in Z. And what should be the case if we're trying to capture less than or equal to? Well, the first coordinate should be less than or equal to the second. Okay, and that is the less than or equal to relation. Let's do another one before we close out this video. We saw graphs already, and we used graphs to do an inductive proof of the Gauss summation formula, but they have the adjacency relation. Oops, adjacency relation. Let's scroll down quite a bit now. And so if I have a graph, remember a graph is just a collection of vertices, and they could be crazy, and then we have edges connecting them. Maybe they are connected in this way. I don't know. Okay, so something like that. And if we were to go in and label our vertices like 1, 2, 3, 4, 5, 6, 7, uh, so what could we do? Well, we could define a subset of V cross V, where V is the vertices of our graph, by AB is in R if and only if A is adjacent to B. So in this picture, we have 1, 2 is in R because there is an edge joining 1 to 2 as we see up there. Let's get rid of that underlining. We have something like 3, 5 is in R. We have 5, 7 is in R. Things that we don't have in R are things like 1, 1. There's no edge joining 1 to itself. There's no edge joining, say, 1 to 5, or really 1 to anything that's not 2, and so on. Okay, so this is another more interesting example of a relation. It's the adjacency relation on the set of vertices of a graph.